A function is continuous at a number x equals to a if the following three conditions are satisfied. First, f of a is defined, meaning there has to be a y value for the given x value. Secondly, the limit as x approaches that value has to exist. And thirdly, the first two have to equal the same thing. In other words, if that limit exists and this limit equals to the function evaluated at that point. Thus, a function is continuous at x equals to a if the limit of f at x equal to a exists and has the value f of a. Wow, that's a lot. But loosely speaking, a function is continuous if the graph of the function is devoid of holes, gaps, jumps, or breaks. So first of all, let's look at some functions. We're going to look at this first one, and this is a given polynomial function. You may recall from earlier lessons that a polynomial has the domain of all real numbers. Right there, that tells you that there can't be any holes or gaps. It's all continuous. You can look at the picture. In fact, I can draw this picture without ever lifting up my pen. So it is definitely continuous everywhere, and no conditions are violated. But let's look at the second one. Very similar to this graph, except there's a big hole. So it's definitely not continuous, but where is that hole? And let's go through those conditions. So it looks like this has a value of -1. So the first thing I ask myself is the function defined at x equal to -1, as in, is there a y value? Well, this hole says there's no y value. All up and down here, I don't see any point on the graph. So this does not exist. So that means condition 1 is violated because f of a is not defined, where a is -1. So let's look at the next picture, or the next graph. So it looks just like the third one. We have that hole there. Ooh, but we also have a point. So going through the same conditions, so we're going to look at f of -1. Is it defined? Is there a point? Yes, there is. It has a y value of -2. So the first condition is satisfied. Let's look at the second condition. The limit as x approaches -1 of our function. Well, going back to a previous lesson on limits, we look as what is the y value getting closer to from the left, what is the y value getting closer to from the right, and it's approaching 4. It doesn't ever get there, but it gets as close to 4 as possible. So condition 2 is met. But what about condition 3? Condition 3 says those have to be the same, and they are not. So we would say condition 3 has been violated because where the function is defined is not the same as the limit of that function at that given value. So let's look at our fourth graph. Obviously discontinuous, there's this big old jump here. Well, where is that jump occurring? It looks like at x equal to -1. So we ask ourselves, is the function defined at x is equal to 1? Yes, it is. This point right here. Remember, that hole says it gets really close to that value but never touches it. But here it's filled in, and that's why it is a function. It does pass that vertical line test. And so it looks like when x is 1, y is -2. So now we look at the limit as x approaches 1 of our function. So again, what is this y value getting closer to from the left? It looks like -2. What about what's approaching it from the right? Well, it's +2. So, do those numbers match? It does not. That means that this limit does not exist, and so condition 2 is violated. One last graph. Obviously discontinuous. You may remember from possibly a previous math class or some previous examples, there's a vertical asymptote there, meaning this graph, this part of the graph is just going to be unbounded, increase, 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 but it never is going to cross over that vertical line of x is equal to 0. So it's definitely discontinuous, but let's look at those violations. So it looks like at the number 0. Is the function defined at x equal to 0? Well, yes it is. It has a big O point right here, and that looks like at -2. But what about the limit as x approaches 0 of our function? That does not exist. This is going way up here, and that has no limit. So this limit does not exist. And so condition 2 is violated. But what if we don't have a graph and we don't have a graphing calculator? Let's look at some algebraic examples. Our examples are going to be limited to what's called polynomial functions and rational functions. A polynomial function is continuous for every value of x. And again, that is something we went back and looked at in earlier lessons. And the domain of all polynomial functions are all real numbers, meaning you can use any value of x and it's all going to be continuous. So this first example is a polynomial, and so let's read those directions because this gets a little tricky in the WebAssign book. State the values of x for which each function is continuous. All right, so this is all values of x. It is continuous everywhere because it is a polynomial function. But a rational function, here, that's a ratio of two functions. Got a big O fraction. You cannot divide by 0. So it's continuous for every value of x where this denominator does not equal to 0. So since it's asking us where it is continuous, it's continuous for every value of x where q of x, or the denominator, does not equal to 0. So I'm going to set that denominator not equal to 0 and solve. So I subtract 1, I divide by 2, and I'm just going to stop there. I could take the square root, but I'm going to get into what's called imaginary or complex numbers. I know that there's no real value that I can square and get a negative number. So where is this continuous? All values of x. Because there is no value I could plug in here, multiply by 2, and add 1 and make it equal to 0. This is never going to equal to 0. But let's look at the next two examples. Maybe that should, again, this one was a little trickier, but we have a rational function. It's continuous everywhere where the denominator does not equal to 0. So I'm going to solve for x. And so it is continuous for all values of x except x cannot equal to 1/3. So in English I would say all values of x except 1/3. But this is a nice fast way to write that answer. Okay, this example, again, we have a rational function, so I'm going to take that denominator and set it not equal to 0. But this is a quadratic. This is why we practiced this earlier lessons. I'm going to factor this. Fairly simple. 2 and 3 multiply to get positive 6, add to get 5. Set each factor not equal to 0. And I get -2 and -3. So this function is continuous at all values except that x cannot equal to -2 or -3, because if I put those values in for x, that would be me dividing by 0, and that is a definite no-no. Now this last one, you're going, well, that's not a polynomial, that's not a rational. This is what's called a piecewise function. We have two different pieces. So let's break it down. I've got f of x is equal to x, which is a line, and I've got f of x equals to 2x minus 1, which is a line. Well, those are also special polynomials, so that means it would be continuous. But when you're looking at piecewise functions, you've got to look at that. It means, hey, it only equals to this when x is less than or equal to 1. It only equals to this if x is greater than 1. So the only potential part where this might be discontinuous is when x is equal to 1. So I'm going to say, well, f of 1 for the first part equals to 1. F of 1 for the second part, even though 1's not included, I'm going to evaluate that function, the second piece, at 1. So I have 2 times 1 minus 1. 2 minus 1 is 1. Since those two parts are equal, when I were to graph these two half lines, they would meet at the point 1, 1. I challenge you to graph this by hand or a graphing calculator, and you would see that these two half lines would meet at the point 1, 1, and so this would be continuous at all values of x. If these would not have been the same values, then it would have been discontinuous at that given value. On some part of your homework, they're going to reword it just a little bit different, and it says determine the values of x for which each function is discontinuous. A little bit different wording. We're going to do exactly the same thing. We've got two rational functions. I'm just going to say equal to 0. I could factor here, but I'm just going to solve by taking the square root, but I'm going to remember to put my plus or minus 3. If you wanted to factor it, you could do that, and you'd have x plus 3, x minus 3, and that's why you would get, again, the plus or minus. So for determine the values of x for which each function is discontinuous, plus 3 and minus 3. I believe in WebAssign it's going to ask you to make a list, comma separated, and that's how you would write that. So just one more try. We're going to set this equal to 0. Again, I'm going to factor because it's a quadratic. I'm going to set both of those equal to 0 and solve for x. And so these are the two values where the function is discontinuous. In other words, it's continuous everywhere except these two values. These two values make it discontinuous. So just to recap, a function is continuous at a number x equals to a if all three of these conditions are met. In other words, a function is continuous at x equals to a if the limit of that function at x equals to a exists and has the value f of a.